Hello, I'm Grace.
I'm Andrea.
And I'm Olivia.
And we are Group 13. Our final project focuses on the effects of low calcium ringers, high calcium ringers, and magnesium ringers on the neuromuscular junction of a frog's sciatic nerve and gastrocnemius muscle. Through this, we demonstrated and examined some of the electrical properties of A-alpha motor neurons in the neuromuscular junctions. Compound action potentials and muscle action potentials were recorded from the sciatic nerve and muscle. From the different solution recordings, we were able to calculate synaptic delay and threshold recruitment. We began by dissecting out the sciatic nerve and gastrocnemius muscle from a frog, placed them in the nerve chamber accordingly, and used stimulating and recording electrodes. The solutions were added only to the muscle, and before each different solution, the whole chamber was filled with plain ringers and a control was taken.
The extracellular recording models the action potentials of both the sciatic nerve and the gastrocnemius muscle. Skeletal muscles are innervated by A-alpha motor neurons whose cell bodies are located in the central nervous system. Together, a motor neuron and the collection of muscle fibers it innervates makes up a motor unit. The motor unit behaves in an all or nothing way, meaning when the motor neuron fires, the innervated muscle fibers will contract in unison or not at all. The space between the motor neuron and a muscle fiber is known as a neuromuscular junction, or NMJ, and is typically in the beginning of the muscle fiber. This is where the map begins and spreads bilaterally. The NMJ is also the point at which A-alpha motor neurons innervate and where muscle starts to contract. The mechanism of the NMJ starts when A-alpha motor neurons are depolarized and send a signal to the PQ-type calcium channels in the presynaptic terminal to let calcium in. The calcium in the presynaptic terminal then causes vesicle exocytosis, carrying the acetylcholine in the vesicles out into the synaptic cleft. The ACH diffuses across the cleft, and two ACH bind to each muscarinic acetylcholine receptors in the postsynaptic terminal at the muscle. The acetylcholine receptors then allow potassium and sodium to flow in, but more sodium flows in because the resting potential is further from sodium's equilibrium potential than from potassium's equilibrium potential. The ACH then triggers an end plate potential, and if the end plate potential reaches the threshold of the sodium channels, a muscle action potential is generated and activates voltage-gated sodium channels on both sides of the end plate potential, causing the muscle to contract. During all of the runs, we recorded cap and map. The cap amplitude represents the number of action potentials and fiber recruitment that corresponds to a certain stimulus voltage, and the map amplitude represents the number of action potentials in the muscle as a result of EPPs, or end plate potentials. During the first control, the cap and map thresholds are the same, 85 millivolts, but the cap keeps rising when the map stops rising, resulting in a lower maximum map, 110 millivolts, than the maximum cap. The reason that the maximum cap is higher than the maximum map is that the cap is composed of all types of subunits of A fibers, including alpha, beta, gamma, and delta. Since A-alpha fibers are more sensitive and have a lower threshold, less stimulus voltage is needed to recruit them, and it takes more voltage to recruit the rest of the fibers. Because the A-alpha fibers are the only ones that innervate the NMJ, the voltage used to innervate it is lower, and once voltage keeps rising past the recruitment of the A-alpha fibers, the muscle is not affected by it anymore, but the nerve is because of the gamma, beta, and delta fibers that are being recruited with the increased voltage.
The synaptic delay in the neuromuscular junction is the time it takes for the release of the neurotransmitter ACH to be released from the synaptic cleft until it reaches the muscarinic cholinergic receptor on the postsynaptic cleft. Three things that happen in between these events are: first, the time it takes for ACH to be released; second, the time it takes for ACH to travel through the synaptic cleft; and third, the time it takes for ACH to bind to the receptors on the postsynaptic terminal. As mentioned before, the ACH is released from the presynaptic cleft when calcium comes into the cell through PQ-type calcium channels, because calcium causes vesicle exocytosis of the vesicles that are carrying the ACH. The ACH then diffuses across the cleft on its own until it finds nicotinic muscle ACH receptors, and 2 ACH molecules bind to each receptor. The way we calculate synaptic delay was through first calculating conduction velocity. This is equal to the distance traveled of the cap divided by the time to travel said distance. This is then used to calculate conduction time, which is equal to the distance between the negative stimulating electrode to the negative muscle recording electrode divided by the conduction velocity. Then, to finally calculate synaptic delay, the conduction time of the cap is subtracted from the map latency. This same method was to calculate all the delays from all the different runs we had.
Now that we've explained the general mechanisms of the neuromuscular junction, we will explain the effects of the different ringer solutions used, starting with low calcium. For the ringers with low calcium, the cap and map threshold were both 70 millivolts, while the map and cap threshold for control 1 was 85 millivolts, or both. The cap and map threshold decreased simply because of the condition of the nerve, and not because of calcium, since calcium was only added to the NMJ and not the nerve. Additionally, the cap and map thresholds are the same because the cap defines the map threshold, since the cap threshold indicates when the A-alpha fibers, the fibers that innervate the NMJ, are recruited, and when the A-alpha fibers are recruited in the cap threshold, their action potentials release ACH through the mechanisms mentioned previously, leading to end plate potentials and muscle action. Map for the ringers with low calcium was 100 millivolts, while the maximum map for control 1 was 110 millivolts. The maximum map decreased in comparison to the control because the ringers had a lower amount of calcium in them compared to the calcium used in control 1. This means that there is less calcium available to go through the PQ channels when the action potential reaches the presynaptic terminal and activates them. Therefore, due to a lack of calcium, which causes vesicle exocytosis, fewer vessels go through exocytosis and not as much ACH is released into the synaptic cleft. When less ACH binds to the nicotinic muscle acetylcholine receptors, less end plate potentials are caused, and a lower amount of action potentials in the muscle are generated, therefore decreasing the map. In regards to synaptic delay, the effects of the ringers with low calcium on the synaptic delay should get a higher synaptic delay. This is because since less ACH is being released into the synaptic cleft, fewer nicotinic channels are reached by ACH, and the rate of depolarization is lower for the end plate potential. Therefore, it takes EPP more time to reach threshold for the action potential of the map. This matters because although synaptic delay is only the time between that it takes from the release of ACH to the start of the end plate potential, we use the time it takes for the map to travel to the recording electrode to measure the latency. Therefore, the time it takes the action potential to occur and reach the recording electrode adds time to the synaptic delay recorded. If, however, we had recorded the synaptic delay with intracellular electrodes, then the effects of low calcium would be only a small increase in the delay because we would record only exactly when ACH is released to when the EPP occurs and not when it reaches threshold or conducts the map through the recording electrode. The synaptic delay recorded for ringers with low calcium should be higher in our results compared to control 1, but it was 1.5 milliseconds in the low calcium ringers compared to 1.7 in the control 1. This is simply because the nerve conduction velocity decreased in comparison to the conduction velocity from control 1. It was 2.8 milliseconds in control 1 and 2.9 milliseconds in low calcium ringers. And dividing a conduction distance by a lower nerve conduction velocity yielded a higher conduction time. Then subtracting the higher conduction time from the map latency decreased synaptic delay. However, if you look at our results, there is an increased map latency of 2.9 milliseconds in the low calcium ringers compared to 2.8 milliseconds in control 1, which ultimately means that the synaptic delay did increase due to an increased depolarization time.
Now we will examine the effects of high calcium ringer solution. The cap, map, and max map threshold amplitudes all increase during the high calcium recordings. For the control for this portion, the cap threshold, map threshold, and maximum map were 70 millivolts, 70 millivolts, and 115 millivolts respectively. The cap threshold, map threshold, and maximum map recorded during the trial with ringers with high calcium were 80 millivolts, and 200 millivolts respectively. The increase in cap and map are likely due to the nerve being slightly dried, as it was not re-soaked between control 2 and the addition of high calcium ringers. The map likely increased as cap increased, as it relies on the propagation of the cap. The max map also increased in our data, likely due to the drying. If the nerve had been freshly soaked, the cap threshold would have likely remained consistent, as the high calcium is not added to the nerve. If the nerve and muscle had also been freshly soaked, with the addition of high calcium on the muscle, it is likely the threshold for MAP would have stayed the same, as it is dependent on the threshold of the cap. The max MAP threshold may have been lower, as and less stimulus is needed to produce it due to the high calcium. If the nerve was happy and the high calcium was added to the muscle, the threshold of the max MAP could have been reached with less stimulus due to the added calcium, triggering a higher exocytosis of acetylcholine from the presynaptic vesicles into the cleft. This higher acetylcholine release means a larger amount of bonding to the nicotinic muscle acetylcholine receptors, therefore a larger influx of sodium into the muscle. This larger EPP could then lead to the MAP reaching its max amplitude with a smaller stimulus. For synaptic delay, the latency of the cap and the nerve conduction velocity for control 2 was 34 milliseconds and 29.4 millimeters per millisecond respectively. The conduction time from the negative stimulating electrode to the negative recording electrode of control 2 was 1.5 milliseconds. The MAP latency and synaptic delay for control 2 were 2.9 and 1.5 milliseconds. The latency of the cap and the nerve conduction velocity for ringers with high calcium was 0.5 milliseconds and 19.6 millimeters per millisecond. The conduction time from the negative stimulating electrode to the negative recording electrode of ringers with high calcium was 2.2 milliseconds. The MAP latency and synaptic delay for ringers with high calcium were 2.6 and 0.4 milliseconds. The synaptic delay decreased from 1.5 milliseconds to 0.4 milliseconds. This is because the depolarization is propagated across the synaptic cleft quicker and at a higher level due to the increased calcium. The added calcium seeps into the NMJ and causes a higher level of exocytosis of acetylcholine from the presynaptic vesicles into the cleft. This higher acetylcholine release leads to a larger and quicker amount of bonding to the nicotinic muscle acetylcholine receptors, therefore propagating the EPP and MAP in return quicker, therefore shortening the synaptic delay.
Now I will be talking about what happened when we use magnesium for cap and map recruitment. For the control, both cap and map were 50 millivolts, and when we added magnesium, it increased to 60 millivolts. Both our max maps were 75 millivolts. This shows that magnesium did not have an effect on the muscle, which is very strange. So what is actually supposed to happen is that magnesium is supposed to decrease the amplitude of the map. And this is supposed to happen because magnesium blocks both calcium. So in high doses, magnesium decreases the calcium entry into the presynaptic terminal, inhibiting the ACH release. So because magnesium inhibits the presynaptic release of the neurotransmitter ACH, it causes it to not be able to bind to the calcium in the cleft. And that causes the MAPs to be reduced, and the effect of the stimulus coming from the ACH prevents contractions all the way to the EPP, causing a lower EPP. So because magnesium should have reduced the calcium release from both the voltage-gated calcium channels and the PQ type channels, the EPP should also be decreased. But in our experiment, there was no change. So now, a few theories that we have as to why this happened is that maybe when we were stimulating our frog, maybe the muscle jumped and that caused there to be an error. That caused there to be an error showing in the no change effect. Also, another theory that we have is that maybe when we were soaking our frog with magnesium, the muscle, we didn't soak it for long enough, also showing the no effect. And also, these are both mechanical effects, And some physiological explanations can be that because the magnesium competes with calcium at the presynaptic membrane, maybe both of these interfered, causing the results of no change. And also another thing is that because magnesium is not a great ligand binder, maybe in this situation, it didn't completely block calcium, nor in any channel, allowing for there to be no change. Now, for synaptic delay, during this part of the experiment, it actually did what it was supposed to happen, which is increase. Our synaptic delay increased, although not by much, it did. And this happened because depolarization takes longer to propagate at the synaptic cleft and the EPP. So the time it takes for the actual potential to occur takes longer across, again, the cleft and the EPP. And also, it takes longer to reach threshold to occur. So because it's going through all of the recording electrodes, that time also causes an increase, causing the synaptic delay to increase. So the conduction velocity of our nerve decreased because the nerve is not as happy. The crying frog. The nerve is not as happy since the action potential is not as fast due to the synaptic delay. The latency also increases because it took longer for the muscle action potential to go through all of the electrodes.
This experiment allowed us to view the effects of low calcium ringers, high calcium ringers, and magnesium ringers on CAPs and MAPs when we study recruitment and synaptic delay from my sciatic nerve and gastrocnemius muscle of a frog. Thank you for listening. And this is your friendly reminder
that everything in this class can be explained
through napkins.